think it's, okay, recording has started, nice. So I'll quickly share my screen because I just want to introduce the paper, and then we'll go to talking about some like conceptual background, which I think is important and cool. Can you see my screen, Vahan? Because I just see you, but anyway, okay. So today, the paper I'm talking about is called Graph Neural Networks for Link Prediction with Subgraph Sketching. And to introduce the paper, let's just talk about the problem. The problem is it applies to graph structured data, so data that looks like that can be described as a graph. A graph, like on a conceptual level, is like a collection of objects that have pairwise relationships. So, for example, at NPlan, we look at construction projects, and the projects are given to us in the form of a Gantt chart, which, and the Gantt chart, it has sequencing between the tasks. So, for example, like build the first floor before the second floor before the third floor. So each task, the Gantt chart creates a graph because you have these pairwise relationships of which task has to happen before another one in the data that we use. You also see this type of thing in like molecules. So if you look at a molecule like H2O, the bonds between the atoms are the pairwise relationships there. And this paper is actually about predicting the pairwise relationships between nodes in a graph. So trying to figure out whether there should be one or shouldn't be one. So that's the link prediction problem. And the authors of this paper, what they're trying to do is, recently there's been quite a few methods that have come out that are quite good at link prediction. Some of them are heuristics, which means that they're like these rules of thumb that seem to work quite well. And others are based on learning approaches, and they work quite well, but they're very computationally intense. And they're all, the learning methods that they talk about, specifically the one that they talk about a lot is called Subgraph GNN. The reason why it was developed and why it's kind of like push state of the art in link prediction is because it dealt with a problem related to the expressiveness of graph neural networks that has to do with, they call it in the paper the node automorphism problem. So before going into the paper and the model, I wanted to talk about what a graph or what is node automorphism, and like what is automorphism with graph data. So I'm going to stop sharing my screen, and I'm going to show you on the board, and please ask questions if what I'm saying isn't clear. Because this is kind of like, for me, this was a really important part of the paper from the perspective of it's something to think about in general when you're using graph neural networks, as like what might be a failing when you're using them that hurts, makes your model unable to learn the relationships you want. So let's draw a really simple graph. So say you have in this case, all of the nodes are the same. There's no differentiation between them. Can you see the graph on your screen? Yes. Okay, cool. And the edges are undirected, which means that there's no way that they're not pointing from one to another. For the purposes of this explanation, let's give the nodes an arbitrary ordering, like 1, 2, 3, 4, 5. And the idea of an automorphism is a mapping from one graph to another, where the mapping maps nodes. So this isn't an automorphism, but one mapping could just be the identity mapping. Actually, this is an automorphism. 2, 3, 3, 4, 4, 5, 5. So So that's like an idea of an automorphism, is just a mapping. But the special thing that makes a mapping an automorphism of a graph is that the mapping maintains the same connectivity between the nodes in the graph. So I'm not gonna be able to explain it that well, but I want to give you an example which I think will help illustrate it. So this is an automorphism because the connectivity within the graph is the same and for all of the nodes. But another one would be the connectivity of each node maintains the same. So if you map like 1 to 5 and 5 to 1, and then let's just say all the other ones are the same. What you can see is 1 has 3 edges going to 3 nodes, and then 5 has 3 edges going to 3 nodes. So they have the same connectivity. And if you switch them, so if you mapped 1 to 5, so you made this 5 and this 1, the connectivity of the graph would be completely the same, and the connectivity of these vertices would be, or these nodes would be exactly the same. And so there's something called a group of automorphisms. There's a lot of different mappings which you can create or like mention between nodes that can that essentially maintain this connectivity. So this is one mapping. This is the identity mapping. This is another one. And you can actually, the reason why it's called a group is because each of these mappings, you can do one after another and define a new automorphism. So like if you did the identity mapping, this one over here, and then you did this one, them composed of each other would be another automorphism. It's the same one because it's the identity mapping. But that's what makes it a group. But okay, so that's what an automorphism is. I hope that's clear. And then there's another concept with respect to automorphisms, which is called a node's orbit. So and it has to do with this idea of composing automorphism mappings that I was talking about. So there's only a certain number of automorphisms that exist for any graph. And at some point, you'll return to the original graph, like the one that we had here with 1 and 5. 1 and 5, the original one. But when you do that, as you go through it, what happens is the nodes that are interchanged with each other, at some point they'll be back to the original one, but they'll go through other ones. So for example, if you applied this automorphism twice, node 1 would become node 5, and then it would become node 1 again. So this is the orbit of node 1 and the orbit of node 5 as well, because the orbit is like the other nodes within the graph, which you could go through to define automorphism mappings.
Is it right to say like all the nodes with 3 edges?
Yeah, yeah.
Each other.
Mm-hmm. I think it gets more complicated with more complicated graphs. So I think that maybe it would change if this was there or something like that. I'm not sure. I haven't thought about the problem too much, but yeah, I think that's a good way to think of it. So in this graph here, there's 2 sets which define the orbits of this graph, which is, oh, that's a bad curly brackets. 1 and 5 are one of the orbits. Or it's not, sorry, orbits aren't sets, but like each node has an orbit. But anyway, like you could define sets for all of the nodes to define the orbits of all the nodes. So 3, 4. Because just like the other one is 2, 3, and 4, because just like 1 and 5, 2, 3, and 4 are exactly the same as each other. So the reason why this is important is because, and this graph isn't actually a great example for the problem, but I'm gonna remove this. The reason why this is important is because in terms of how GNNs work, node 1 and node 5 would have the exact same representation. Like the exact same representation. So same. So they would have the exact same representation. And that becomes a problem when you're trying to figure out when there should be links between nodes, because links, like we talked about at the beginning, are these pairwise relationships. And so, but actually, I'm gonna draw another example to continue this explanation, which is the example from the paper. I think that will be a little bit more instructive as to why this is an issue. So I think the example they give is and I just need to scroll up to make sure I have the right graph. And then they have yeah.
You want to show it higher?
Is that better?
And turn it a little bit left. Yeah.
Okay. So so this is the graph they give it. Oh yeah, sorry. There should be an extra. This is a graph they give as an example in the paper. And let's order it again, like 1, 2, 3, 4, 5, 6, 7, 8. So here, two nodes that are in the orbit of each other are 1 and 7. And those two, with in terms of a GNN, would have the same representation. And what that means is that if you're trying to calculate the links between those for those two nodes, your model is going to tell you that they should be connected to the exact same nodes. So, for example, if your link prediction model said 1 and 2 should be connected, it's also going to say that 7 and 2 should be connected. But in this graph, 7 and 2 aren't connected and shouldn't be connected. And that's because the representation that's calculated for 1 and 7 is the same. So you need to have some way of distinguishing those nodes in order to be able to calculate links, like to be able to calculate this graph essentially, to be able to have a model that could calculate the links for this graph, or predict the links for this graph. So that's the problem that they're trying to address here in this paper, which is that normal GNNs have this, if two nodes are what they call automorphic, which means they have the same, they're in each other's orbit, then you're not going to be able to distinguish between them with your model, and so you're not going to be able to predict a lot of different graphs that have these types of links in them. Just to give you an idea, one trivial way that they suggest that you could deal with this is you just number each of the nodes arbitrarily, because then you have a way of distinguishing between them. Then 1 would be connected with 2, and 6 would be connected with 7. But the problem that they point out with that method is that it struggles to generalize to new graphs. So anyway, that's like the kind of the theory background behind this paper. Maybe not theory, but like the conceptual part of this paper and the problem that they're trying to address. I'm going to share my screen now so we can go through it. Actually, before that, does anyone have any questions about what I just presented?
Maybe I didn't understand like why 1 and 7 will have same representation.
Okay. So if you looked at 1 and 7, I'm going to take away all these numbers.
essentially the graph is symmetric.
Yeah.
Right? You can flip it, and then it's the same graph.
Yeah, so that's what Vahan said is true. It's that the graph itself is symmetric. So this node, which was 7, and this node, which is 1, they look the same to a GNN. What?
Also to us, we can just rotate. It's the same graph.
Yeah, that's true. But we're not the ones who are doing link prediction. The model is. And so when you have this type of similarity that the GNN and a GNN can't tell the difference between these two, it would be impossible for it to say that like this node should be connected to these nodes and this node should be connected to these nodes. Instead, what would actually happen is that it would say this node should be connected to these nodes as well, and this node should be connected to these nodes as well. Oh, not that one, that one. So you wouldn't be able to recover that graph because of this symmetry. Yeah, well, as we go through the problem in the paper, hopefully it will also become a little bit more clear. It took me a while. I was introduced to the idea of graph automorphisms. I've been introduced to it multiple times, and it's still kind of like a really heady concept for me. I can see the importance of it towards this problem, but I do think it takes a little bit of time to understand and why it applies here. But okay, where's my cursor? Okay, let's dive into the paper. So we kind of talked about like what is the problem that they're trying to address here, which is find a model that that's able to calculate representations that are unique for nodes that are automorphic, so that you can actually perform good link prediction for these nodes. And the thing that they point out is that there is a model that does this, which is called subgraph GNNs, SGNN over here. Oh, I'm going to zoom in quite a bit because I don't think, hopefully you guys. The only problem with preview is a little bit, which is this, should I zoom in more or is this good? I'm going to assume it's good. Okay, so they call it SGNN. And SGNN, the way that it works is that it will take a link, or actually it will take a node. It has multiple steps. Let's see, where are the steps described? Because I'll just read them out, and then you can also read them as I say them, which I think is better. Subgraph GNNs. Okay, here's subgraph GNNs. And okay, so subgraph GNNs, the method that they're kind of, they start off with. And just so you know that one of the things that they're doing here is they're saying subgraph GNNs is a model that works quite well, but it's incredibly computationally intensive. So how can we find a model that's much simpler, that works just as well and is based on the same ideas? So what are the ideas in subgraph GNNs, SGNNs? The first idea is subgraph extraction around every pair of nodes for which one desires to perform link prediction. So we usually think of a graph as a single graph, or a node and that has nodes, but the way that you would express it here is that each node in the graph would have its own subgraph, which is a subgraph which is like the k-hop neighborhood of the graph. I think that's what they're using, which means that it's all the nodes and the edges within a certain distance from the link, which, so for example, if the distance was 1, it would be all of the nodes that are 1 edge away, and those edges from the original node or the original link, or sorry, the original link, all the links that would array from there. So you extract that subgraph, and then you augment that subgraph by adding structural features to it. So it's what they call structure features. A structure feature could be something like the number of cycles in the graph, or the number of triangles in the graph. Supposedly there's the heuristics that are used for length prediction that are really good and rely on counting triangles in these subgraphs. So, and we'll go over some of them that they use. All of the ones that they're looking at are like these distance-based structure features, and we'll go over that. So you extract the subgraph for the length, then you augment it, meaning for all of the nodes in that subgraph, you add structure features. And then finally, after that, the third step is you perform feature propagation over that subgraph. So you have your original node features, and then the structure features, and you use like a GNN to propagate information through that subgraph, and then you use, which is step 3 over here. We're looking at this paragraph. Sorry, I should make that clear. Looking at this paragraph. I won't let me. This paragraph. And then, so step 4 is you learn, you have a graph level readout function to predict the length. So the subgraph that you've created and then passed information through is supposed to be a representation of the length. So you have to summarize that graph level function, that subgraph which has nodes and edges into like a single vector representation, and then calculate like the likelihood of there being a link. And so that's what this graph level readout function does. And so you have these 4 steps, and what they're trying to do is determine the importance of these 4 steps with the set of experiments we're about to go through, in order to determine like what was actually important for the performance of this method, and whether you can make the method itself a lot more computationally tractable, like reduce the amount of computations that are required. So the first thing they look at is actually, instead of looking at the subgraph, taking the subgraph, what they do instead is they look at structural features. So they talk first about like the different structural features that are calculated. That they use. They look at 3 different methods. One is called 0-1 encoding, one is called double radius node labeling, and one is called distance encoding. And all of these things would provide a node with some kind of structure features, which would help you distinguish, as in the examples we were looking at, like node 1 from node 7 in the problem that we saw. So I'll just quickly say which, where is it? I'll quickly say what each one does as they describe it. Actually, I won't go into too much detail about this, but essentially, all of these different methods, they use a distance like between nodes as like the inputs, and then they have some kind of process function that processes it to come up with a representation of structure features. So, for example, in distance encodings, each node, which is their DE method, each node is encoded with a tuple, which is the distance between one of the nodes in the link, U, and J, and one of the other nodes in the link, V and J, where J is multiple different nodes. Like it might be all of the nodes in the subgraph. So you create like a tuple for all of them. And so you have all these methods that are distance-based methods, but the thing to know about it, these structure features, they're just telling you information about the structure of the graph in the local area of the node with respect to that node. Yeah. And a key point of what I just said is that it's the structure features are with respect to the local area around that node. And one of the first experiments they do, which is over here, is the importance of the different features calculated by this structure representation, based on their distance from the, yeah?
You see this video? No. Oh, I can't see the video.
Wait, can you see the,
No, no, but not minimize it. Can you want to see it?
can you guys see the paper or no?
The page 4 of the paper.
Okay.
Yours is, okay, good. I was like, oh my God, I hope you guys can see what I'm seeing, otherwise it would be. These structure features are based on the local area of a node, and you can define local as a certain number of hops away, or it says like a certain max distance r, where like r of 1 means a distance of 1 away, r of 2 means a distance of 2 away, and so they want to find like they want to find the importance of features, structure features that are a certain distance away, and they use this as an experiment to do that. But like the main point is that they're doing link prediction with the structural features, and they find that the most important features for doing link prediction are the structural features that are within a radius or a distance of 1. So you can tell that by feature importance. It's really high for 1 and lower for 2, 3, 4, and 5, and that's for these different methods. So a key point here is that you really don't need to see a lot of the structure features, at least for these data sets, like far away from a node to get a good structure feature representation for each node. That's like one of their first insights, and it's important because it means that you don't have to sample such or extract such a large subgraph for each node in order to see the effectiveness that you saw with SGNNs, because they were looking at larger subgraphs. So the next thing that they're talking, and just to be clear why I'm focusing on this, it's like because that section was about structure features, but it's also talking about actually sampling subgraphs, which is step 1 of subgraph GNN, getting a subgraph for each node. And it's showing that you don't need such a big subgraph, and then these are the structure features that we used, which are important, and they are important for performance. I think they have over here, yeah. Over here, they show you the link prediction performance of a model when you're using none of the structure features, and then how it performs when you use any of those 3. Seems like for these 3 data sets, DRNL works the best. But you can see that the performance is quite low, like 20% worse in one case when you don't include the structure features. So structure features are important. You don't need to have such a large neighborhood to calculate them. And then the second step is that, so once you've calculated, you've gotten your subgraph and you calculate all the node features and structure features, you want to propagate them through that local subgraph to get a representation that encodes that subgraph. And this, for me, was one of the most interesting results of their experiments, which is what they found was that it's actually better not to process the structural features at all, so not to propagate them through the graph, so basically not to put them into a GNN. And you just leave them as they are. And that, but also for the node features that were originally there for the node, like what they found was that it's really useful to just perform message passing without any parameters. Like with that, so basically, if you guys know about GNNs, a GNN is there's a little bit of, you could switch this around, but it's like you have these features for each node, feature vectors. You perform message passing on them, which means that you aggregate all of the different feature representations, and then you have some kind of aggregation function like max, mean, whatever, and then you pass that through a linear layer and an activation function. So they found that just passing and doing it for one hop, just passing the node features through a message passing layer and doing an aggregation was good enough in terms of the propagation step. So the part that's really interesting to me about this is that you don't, and this is true of their final model. Their final model doesn't include any parametric, like there's no GNN in their final model, essentially. It's just a pre-processing step of their model is they do this feature aggregation, which is shown over here, which is they're just taking the average of the neighbor's nodes. So propagation through the subgraph is actually not that important. And then the final step or the final part of their, yeah.
Maybe I missed that. How big are the graphs? What sort of graphs are they? Maybe it depends on the type of graph.
So right now I don't know how big the graphs are. They did it on 3 different data sets, which is Quora, CiteSeer, and PubMed. But they're talking about propagation within the subgraph that they're talking about for each node. So that's a much smaller graph.
Right, maybe that's why it makes sense.
Yeah.
If you average everything in Quora, then it doesn't make sense, right? Right. And then, do you know how big are the subgraphs?
I think it's a heuristic. I mean, it's a parameter, like choosing the number, how big they are.
I mean, is it all
But I think like three I think is the max or something like that.
That makes sense.
Yeah. And then finally, they have the final part of the SGNN, which is the readout function, which needs to summarize the whole graph so that you can perform link prediction. And what they actually do is they just take the representation of each node from that subgraph as it was calculated through all of this pre-processing. And in the link, they put them together, they concatenate them, and they put them through an MLP. I mean, and so the point that they make in this section is that one thing you could do is you could take the mean of all the node representations or the sum of all the node representations in the graph, but it actually works a lot better to just use, no, sorry, maybe it doesn't work a lot better. I don't know if they have, where's figure 2b? Yeah, it does work a lot better for one of the data sets. For the other two, it doesn't seem to matter as much. You can see mean, sum, these are graph pooling operations and then edge. But basically their point is you don't have to do this sum or mean. You can just take the representation of that edge based on its 2 nodes, which is a lot more computationally efficient, and use that as the input for your readout function. So that's another place where you can get some computational savings by just doing that instead of having to do this averaging. So here's the summary of the results from all these experiments. Structure features are important. The process of embedding them and propagating them with the SGNN is actually not great for efficiency or performance. Most of the structure features that are important are quite close to the node, so you don't need to look that far out. And an edge level readout is good for the readout function. Okay, so then they talk about, how much time do I have left? What time is it? 20 minutes, okay, cool. So then they're finally talking about, not finally, but now they're talking about their method. So they want to create a method that's like SGNN, but takes into account these insights to make it as expressive, but a lot more computationally efficient. And the way they do this is like they instead of having to sample a subgraph for sample, I keep saying sample, not extract a subgraph, k-hop neighborhood subgraph from the graph for each node, you actually just calculate these node level features. And it's a lot quicker. The features are here, it says that they have let mathcal A for this link be the number of distance labels for link UV, which is equivalent to the number of nodes at distances DU and DV for U and V. So the representation that they use is of structure features is the count of how many nodes are a certain distance away from a node. So for example, if you had a node that has 3 edges connecting it, then the count of distance 1 would be 3. And so they do that for multiple different distances. I think they cap it at 3 or maybe 2. And they also have a count of how many nodes are that farther away than that. So if there were 100 nodes in the graph and a node is connected to 3 nodes, then the distance count of 1 would be 3, and then the distance count of everything farther away would be 97. And so they create these feature vectors of counts for each node based on distances of other nodes in the graph. And that's how they describe structure features. But that's actually pretty computationally intensive, especially if you want to do it live. And I think all of these, all of the people who are working on this work at Twitter, where they're working with, if they're doing like the graph of the connectivity of Twitter, it's probably like millions or billions of nodes, or hundreds of millions of nodes. So this is why they have such a huge focus on making this computationally efficient. So this whole section, this next section, which I don't really want to go into, is talking about different ways of calculating these counts very quickly. You're approximating them, but with the methods which they're using, which are hyperlog-log and min-hash. But essentially, you can think of it as the feature vector is counts of nodes and how far they for any node, it's a count of how many nodes are within a certain distance and how much and farther away than that distance.
At this point, we're talking about the whole graph.
Yeah, you're talking about the whole graph. Yeah, it's a good question. And so here's where they've introduced their structure features and all of that. And here's where they introduce their method ELF. And so I think L is for the number of layers in the graph and in the model. And so for each layer is calculating a new M and H, which is actually just used to calculate these estimated feature counts over here, if you read the previous section. So each layer is updating their structure representation for each node. And then all you do at each layer is you take the node representation of U and then V for, so basically you have a function which is probably like a linear layer or an MLP that takes, for any node U, it aggregates its, it takes its neighbor's representation V, its representation V, and then the structural representation of the edge E, processes it through an MLP, and then performs an aggregation step, and then concatenates that with the previous representation U's representation and puts it through another function. Very similar to a GCN, except that in a GCN, you wouldn't have this or this. So you wouldn't have the node's representation or the structure features for calculating this representation over here. So that's their model ELF, and when at the end of it, so like after L steps, they also, what they do is they have the readout function, where their readout function just takes, for any pair of nodes, it takes the feature representation of the node representation of node U and V, and does an element-wise product, and then also gives you the E for that edge, so the structure representation, and they just use an MLP for that. So let's see. I have to be honest, I am worried that I'm not explaining this part, equations 7 through 9, that well, because I'm thinking either L is like a depth. No, it's not a depth. It must be the layer. I know this is pretty standard notation too. Well, it does say up to an L-hop neighborhood, which is used.
So that's the layers.
Yeah, I guess it's both like distance and number of players.
As you go deeper, I think your visible range also expands proportional to L, right?
Yeah, yeah. So yeah, anyway, so you propagate through the graph for L layers, which means you see a neighborhood that's like L hops away, and then you use the representation that's calculated in order to calculate the likelihood of every link that you want to know about in the graph. What is interesting about all of this is that, okay, if we look through here again, they've described the readout function up to where it says figure 2b. One of the insights they say over here, where my cursor is, it says GNN propagation is either not needed or can be processed globally. Structure feature can be generated from sketches instead of subgraphs. Edge pooling and readout functions perform well as graph pool readout. Okay, yeah. Anyway, this is ELF. I'm getting ahead of myself because this is the model that they propose. Then they have some theory showing that it's more expressive than a message passing neural network, that it can distinguish graphs better than a message passing neural network. That's what these propositions are. And yeah, and then they introduced Buddy. I like Buddy. Buddy is their more computationally efficient method because it moves all of the computationally inefficient parts of the method to pre-processing. And in this method, they don't do any message passing. Like, so, well, they do it as a pre-processing step. Over here in ELF, there's like a lot of, there's two parameterized functions, phi and gamma, which are used before you go to the readout function, which is psi. But in Buddy, they just do all of the pre-processing offline, and they do message passing without any parameterization. So essentially, they calculate like what I consider to be kind of a heuristic, but a heuristic that is quite well informed by theory for a feature representation of each edge. Because everything here in this feature vector, in this line, is calculated without any parameterized function. Nothing is learned at this point. This is all just feature processing that's done based on like analytical equations and so on. And then they just use an MLP. They learn an MLP for Buddy that takes this feature representation and outputs an idea of link predictions. So, and one of the points that they make is if you look at the results, which are over here, they show you the results of 3 heuristics, CN, AA, RA, and then quite a few different methods. SEAL is like state of the art, and NeoGNN are state of the art for link prediction. And so red means first place, blue means second place, and purple means third place. You can see Buddy gets first or second place on every single data set, which I think is really impressive because like they're using a very shallow MLP or a small MLP to do link prediction with like just feature prediction, just like feature pre-processing, and they get really good results with Buddy. I don't even like, it's just crazy. There's very little. Most of the feature processing is done without any learning, and it does so well, which is really interesting. And I wonder if this is going to lead to like a new set of GNNs maybe that have a lot of this information in it, because it just performs so well without any learning, or with a much simpler model than the ones we've been using up to this point. And if yeah,
is there something that this sort of says then, is that like there was more information in the node and edge features than was properly being extracted by those more complicated.
Yeah, exactly. It was that GNNs were not able to pick up on the structure features within the graph that were actually really useful for predicting links. And now they found a way to calculate it, but calculate it without ever having to learn much. So we'll have to see what this paper leads on to next, because originally I was like, well, the results aren't that much better than previous methods. But then another thing you have to look at is how much faster this model is and how much simpler it is. It's so simple. I mean, okay, the pre-processing and the theory behind it is quite complicated, but but it's, in my opinion, it's quite simple. And then look how much faster it is to perform different steps. So Seal is state of the art on PubMed, and the static one, which allows inference to not take 23 seconds, requires about 10 minutes of pre-processing. Buddy requires 5 seconds of pre-processing, and Seal still takes 9 seconds to do inference, whereas Buddy takes 6 milliseconds or 60 milliseconds. So it's like more than 100 times faster. So anyway, this paper is really cool because it's able to create learn a really simple model with good feature preprocessing based on theory to create a much faster link prediction model that's also more accurate. So I think it's a really cool paper, and I'm excited to see what the follow-ups are to it. So thanks for, that's all I got. But if you guys have any questions about anything, now's the time.
How long is 3 million seconds? That Seal static on.
Yeah.
I have one, I guess 2 comments. Did they do any experiments when they were going up to the? That would be interesting.
I don't know. I honestly don't know whether these are. Do you think these are all transductive? PPA. Let's look at the experiment section. Yeah, then it was inductive.
Because PPI, we know PPA.
Protein association.
Similar. So each graph is a protein. So they did that too.
Yeah.
So I was thinking it might not work as well, because in a new graph, structures might be very new, right? So we need to do something about maybe it doesn't work as well.
They talk a little bit about that in the paper, but honestly, I think I'd have to study it more to understand that aspect of it.
Something to do. I think it's between proteins.
Yeah, each protein is a graph, and then there's a node, and then the graph.
Yes.
They also
It's one graph.
They also released a library, a PyTorch-based library for doing this. So hopefully the code is well written, but
It's from OGB. This, probably still constructed.
Yeah.
The other question was, did they mention reverting the graph? You know what you did? Having edges and nodes and learning on that.
no, they didn't mention that, but indirectly they introduced the concept. I actually was. I was thinking that it was. Yeah, they do. What?
Because on a massive graph of billions of nodes, that might be very expensive.
I can't find it exactly, but there's a point when they talk about how there's such thing as automorphic links and automorphic nodes. And the point that they're making there, sorry, I'm not going to be able to find it, so I'm just going to scroll up to the top and discuss it. So in order for you to understand the concept of automorphic links, it means you have to have thought of the graph in the inverted way, because it doesn't make sense to have an automorphic link unless you invert the graph so links are nodes and nodes are links. So for anyone who's wondering, you can like I said before, a graph is a collection of objects and pairwise relationships between them. So the pairwise relationships are the links, but you could also invert the graph So the links are nodes and the pairwise relationships are the nodes. And if you did that, then you could get the idea of an automorphic link, because then the link would be a node in that case, and it could be automorphic, which means that it would have like other links in its orbit and so on. Yeah.
Do that though, because each edge is associated with two nodes, right?
Mm-hmm.
But each node is not necessarily associated with two edges.
Yeah.
It's associated with many edges, right?
Yeah.
So how would you then?
So that's how the node connects those edges. So if you had like one edge and then two other ones, this edge would be connected to the other two because of the node. So the node defines multiple links.
Okay, so in your inverted graph, an edge may become several.
Yeah.
Several.
Or a node might become several
A node might become
links or
several
edges. Yeah.
Yeah, then if you have a node with many edges, it would become a very dense graph.
Mm.
If you not opposite.
Yeah.
I wanted to ask a slightly different question.
Mhm.
Is what they're using this for at Twitter? Is it kind of like a somewhere to start with suggested friends sort of thing, suggested follows?
I
Like,
don't.
if each node was a person, and there wasn't, because I imagine they've got this big graph of people who are following each other. Is it like there is no edge between these two people? What is the likelihood that there should be? Like, are they ever interested in when there is an edge and trying to predict when there shouldn't be one? Or is it mainly about trying to take a graph and look at node pairs where there's no edge currently and say there should be one?
So the researchers in this paper, they look at graph problems from a very abstract point of view.
Okay.
So they don't even mention how they're using it at Twitter. It's more just like in the general case that you want to perform some kind of link prediction. They actually motivate it with drug discovery and knowledge graph construction. And also they point out that it can be used in recommender systems. And what you're talking about is a recommender system, in my opinion.
Yeah.
So probably it probably is how it's being used.
Okay. Yeah. I guess, yeah. I'm trying to understand a bit, like, would they ever run this sort of thing between two nodes that they know there's an edge between already?
I don't think so.
No.
Yeah. Because they already know that there's an edge there, so they don't need to predict it. It might be interesting. Maybe there's some kind of like retrospective analysis you could do. Like, this is a really unprecedented connection or something like that.
Yeah, because I think, yeah, maybe there's fields where that would be interesting. Right?
Yeah.
You do want to know if there's an edge there that it shouldn't be there.
Yeah.
Or it's unusual.
Or like maybe how two communities are connected such that they're sharing information when you wouldn't expect them to. Like who's the person in ML who's helping, or not helping, but like passing information to the study of swarms, like in biology or something like that. I think there might be something in the chat. I just need to find my cursor. Okay. Okay. Well, thanks everyone for coming and for attending this session. And I hope we'll see you all next week. It's going to be remote next week. And have a good weekend.
It was very good.